Welcome to the end of Cycle 4. So we have finished, by this point, Book 1 of Introduction to Arithmetic, and that's as far as we're going to go with Nicomachus. And I hope that you've enjoyed it. But these last few chapters have been fairly challenging. So we'll talk about these today, and we'll see if we can clarify some of the concepts. Now, the things he discusses in these last few chapters regarding the 10 divisions of relative quantity, they're not really complicated concepts. They're actually fairly simple. He just expresses them in difficult language, and I hope that my introductions were helpful in helping you decode some of that. But we'll talk more about it today, just to make sure that all that's very clear. We'll also go over the study questions, as always, and the drills, with the exception of the drills from Mathematics for the Non-Mathematician. Now, if you haven't already discovered this, there is an answer key in the back of Mathematics for the Non-Mathematician for all these exercises. So if you look at the end of Epicycle A, you had those two sets of exercises for Mathematics for the Non-Mathematician. And you should be able to find the answers in the back of your book for those. And so if you haven't taken a look at the previous exercises that we did for Mathematics for the Non-Mathematician, if you haven't gone back to check your work there, you might want to do that today as well, just to make sure that you've done everything correctly so far. It's always a good practice to pause and make sure that everything that you think you've done correctly has actually been done correctly. You don't want to go forward with mistaken ideas. That can lead to additional confusion later on. So make sure whenever you can that you're checking your work as we go through this. All right, so let's go ahead then and start by looking at Chapter 17. Let's start with the study questions for Chapters 17 and 18. Now, the answers to these are really found in Chapter 17, so go ahead and turn there. The answer to the first question, what are the highest divisions of relative quantity? The answer is found there in paragraph 2. Of relative quantity, then, the highest generic divisions are 2, equality and inequality, for everything viewed in comparison with another thing is either equal or unequal, and there is no third thing besides these. So the answer to this question is that everything is either equal or unequal. That is the fundamental distinction of relative quantity, which I will also label. So we'll write up here the highest division of relative quantity is between the equal or the unequal. And this should make sense, right? The most fundamental thing you can say about two quantities is either that the quantities are equal quantities or that they are unequal quantities. All right, let's take a look at the next question. What are the 5 species of the greater? Now, the 5 species of the greater, these are listed in paragraph 7. And I'll type them up as we read through them here. So we have moreover of the greater, separated by a second subdivision into 5 species. So we'll place that here. So the 5 species of the greater are the multiple, then we have the superparticular, the superpartient. Now we have the multiple superparticular and the multiple superpartient. So those are the 5 species of the greater: the multiple, the superparticular, the superpartient, the multiple superparticular, and the multiple superpartient. Next, we have the 5 species of the less, or 5 species of the lesser, and those are listed in the very next sentence. And he says, and of its opposite, the less, there arise similarly by subdivision 5 species opposed to the foregoing 5 varieties of the greater, and then he lists them. Have the submultiple, the sub-superparticular, so basically the subversions of the other ones. The sub-superpartient. Then we have the submultiple superparticular and the submultiple superpartient. So we've got the first division is things are either equal or they're unequal. If they are unequal, then they're either going to be greater or they're going to be less. And if they're greater, they're either going to be multiples, superparticulars, superpartients, multiple superparticulars, or multiple superpartients. If they are less, then we have the submultiples, the subsuperparticulars, the subsuperpartients, the submultiple superparticulars, and the submultiple superpartients. And those are the 5 species of the greater and the 5 species of the less. So let's move next to the response exercises for epicycle B. So here I ask you to, in your journal, show that the claim made in paragraph 19 is true by performing the calculation with the heteromechic numbers for all 10 perfect squares on the diagram in paragraph 9. So you know that there's that beautiful diagram that lists all the numbers. I'm going to sketch out part of it here. But basically the diagram is you have 1, 2, 3, 4, right? It's this diagram. Basically, you might know this as a multiplication table, and it just keeps going on and on and on. Now, down the diagonal, down this side, we have all the perfect squares. So 1, 4, 9, 16, those are the perfect squares. Now, the heteromechic numbers, and maybe this wasn't clear, but I hope that, that my footnote was helpful. The heteromechic numbers are these. So 6 and 6 are heteromechic numbers with respect to 4 and 9. And so you can think of it as drawing a little box around the perfect squares, and the other numbers that fit inside that box are the heteromechic numbers. So you can also do this over here, 9 and 16, those consecutive squares, 9 and 16. That means that the heteromechic numbers here are going to be 12 and 12. And so I'm not going to do all of them. I'll just show you an illustration with these two, in hopes that that will allow you to go back and check your work for the other ones in case you were confused on how to do this. So the claim he makes in paragraph 19, I'll read that for you. So chapter 19, paragraph 19, he says, the terms on the diagonal from 1 to 100 are all square numbers. The products of equals by equals, right? This makes sense. 4 is the product of 2 and 2. 9 is the product of 3 and 3. He says, and those flanking them on either side are all heteromechic, unequal. In other words, these are heteromechic. 6 and 6 are heteromechic numbers because he says that they're unequal, but they're unequal in the sense that 6 is the product of 3 and 2, and 3 and 2 are different from each other by 1, right? 2 and 3, the difference between 2 and 3 is 1. And you find that this is also true of 12. 12 is the product of 4 and 3. So 4 times 3 gives us 12. And 12 is a heteromechic number because the numbers you multiply to get 12 in this case, 4 times 3, are different by 1 as well. And so that means that the product of 5 times 4 will also be a heteromechic number because the difference there is 1. So 20 will be a heteromechic number. Similarly, 6 times 5 is equal to 30. That will be a heteromechic number. Now, if you turn back to that chart in your book here on paragraph 9 in Nicomachus, you'll see that this is true. If you look at 20, you see that it's on either side of the consecutive squares 16 and 25. 30 appears in that little, if you were to draw a box around 25 and 36, the next two squares, 30 would be the heteromechic number there fitting alongside it. So that's what it means for numbers to be heteromechic. They are almost squares in the sense that they are almost the products of equal numbers, almost. The numbers are unequal by 1, and that's what makes a heteromechic number a heteromechic number. Now, you might be thinking, yeah, but don't these numbers have other factors as well? They do. You can also take 12 and get 12 by multiplying 2 and 6. 12 is still a heteromechic number, even though when we multiply 2 and 6, that isn't immediately clear. But the fact that we can get 12 by multiplying two numbers that are different only by 1 makes 12 a heteromechic number. So 10, in other words, is not a heteromechanic number because there are no factors of 10 which are exactly 1 apart, right? The factors of 10 would be, you've got 1 is a factor of 10, because 1 times 10. 2 is a factor of 10, it's 2 times 5. And then 5 is a factor of 10, and then we're out of factors, right? And so 10 is not a heteromechanic number, because to get 10, you have to multiply 2 and 5, or 10 times 1, and none of those are exactly 1 apart. Now, if you're thinking about this carefully, you might also have noticed that the number 2 is a heteromechanic number, because how do you get 2? 2 times 1 gives you 2. And sure enough, if we draw a box right here, this proves that 2 is in fact heteromechanic because it flanks the perfect squares 1 and 4. All right, so that's what we have so far. Now, to prove what he's talking about here, we can just run through a few cases. So let's go back to paragraph 19 and finish reading it. So he's talking about the heteromechanic numbers. He says, and those flanking them on either side are all heteromechanic, unequal, and the products of the sides of which one is greater than the other by unity. So as I said, the way these are heteromechanic numbers because if you were to draw them as rectangles, right, let's just take 6 for instance. If you were to draw 6, a rectangle of 6, you'd have a side of 2 and a side of 3, and the difference is, as he says, a difference of unity, right? So the difference there would be a difference of 1. For that reason, those are heteromechanic. And so the sum of the 2 successive squares and twice the heteromechanic numbers between them is always a square. This is the claim I wanted you to analyze. And conversely, a square is always produced from 2 heteromechanic numbers on the sides and twice the square between them. So to prove this, or to show what he's talking about, let's just take a look at this first case with 4 and 9. So he says, if we add these together, we should get a square. So let's just do that. So, and he says twice the heteromechanic numbers, which really just means adding the 6 and this other 6, or you can do 2 times 6. But it's not 2 times 6 and 2 times 6, it's just either both of these or twice the 1. So the way that we do this is it's 4 plus 9, so there are both of our squares. And then we're going to add the 2 heteromechanic numbers as well. So we could do 2 times 6, but I'll just write them out individually, because I like visualizing it this way better. All right, so if we add this up, this should give us another square. So 4 plus 9 is 13, right? 13. And then 6 and 6 gives us 12. And so that obviously gives us 25. As it turns out, 25 is indeed a square. It's the product of 5 and 5. So that works beautifully. So if we add up all the numbers inside this little box, we discover that we've got a square, which is a really cool relationship. And the same is true if we do the next one. So let's try that. 9, 16, 12, and 12. Let's add those. So 9 plus 16, add the squares, plus the heteromechanic numbers that flank them, so 12 and 12. And we find 9 plus 16 should be, what, 25? Plus 12 and 12 should be 24. Add that up, and we get 49, right? That's another square. That's the product of 7 and 7. So 49 is another square. And this works with every single one. Now, the amazing thing here is that the relationship continues even beyond what Nicomachus has laid out for us. And I'll see if I can show that to you. Okay, so I've switched colors, and now I'm going to draw a different box. Let's draw this box here. So what if we make the box a little bit larger to encompass 3 squares? So we've got 4, 9, and 16. And that would make 6 and 12 the heteromechanic numbers. And 8 is not a heteromechanic number. But what happens if we repeat this pattern? If we add 8 along with the other numbers that fit inside this larger square, are we still going to get a square? Even though 8's not a heteromechanic number, we're taking the same procedure, and we're just expanding it by drawing a bigger square with the diagonal here, with the squares on the diagonal. So let's see what happens. So if we take this, we have 4. I'm just going to add them up row by row. So 4, 6, and 8. 4 plus 6, that's 10, plus 8 is going to give us, plus 8 is going to give us 18. The top row is equal to 18. I'm adding up in stages just to make it easier on myself. 6, 9, and 12 should give us 27, 8, 12, and 16. Oh, this is interesting as well, isn't it? 8, 7, 9, 1, 2, 3. That's an interesting pattern, which may be worth actually following up later. I'll leave it up to you to explore this pattern, because the ones places as we go across the columns, as we add them up, the sums go 8, 7, 6, and the sums of the tens places go 1, 2, 3. But I'll leave that for you to explore on your own. Okay, so we've got this so far. Let's add up all these numbers. So I'm just going to do this longhand here. So we've got 6 and 7 and 8. That should be equal to, let's see here, 21, I believe. Just double check. 6 plus 7 is 15, plus 6, 21. Okay, then here we have 5, 7, 8. Double check. 3, so that's 3, 6, 8. That's all correct. And do you see what the sum is? The final sum is 81. That is a square. 81 is a square of 9. So even if we expand the square and add up all the numbers inside the square, as long as the diagonal follows the perfect squares, right? We still get a square, which is amazing. So not only is this true with the heteromechanic numbers, but if we expand it, it remains true. Just one of the many amazing properties of this particular table, this multiplication table. And Nicomachus even makes the point. He says, if you're a clever person, you can continue to look at this and find all kinds of other amazing properties, but he doesn't go into the other ones. He just says, there's lots of other stuff here, but he doesn't touch on it. This is just one example of how you can continue to find amazing things in this table. So let's next move on to the next response exercise, which is to copy out the following 8 fractions and analyze them to determine whether they are superparticular or sub-superparticular or neither. So let's write those fractions out and then we will analyze them. I've written out all 8 fractions, and underneath them here I'll be writing out their equivalents, and after we do that we'll go through one by one and we'll talk about what it is. So first, let's just reduce these to their simplest form. That's always a good way to begin. So 36/48, this needs to be reduced so that we can really analyze it, simplified. So we can do this by dividing each number by 12, right? So if we divide 36 by 12, we get 3. If we divide 48 by 12, we get 4. So 36/48 is equal to 3/4. 65 and 52. As it turns out, 13 is a factor of both, and maybe that was a little bit difficult to figure out, but 13 times 5 will give us 65. So if we divide 65 by 13, we get 5, and if we divide 52 by 13, we get 4. So 52 divided by 13 gives us 4, 65 divided by 13 gives us 5. So this fraction is equal to 5/4. Next, 30 divided by 15. Well, as it turns out, 15 is a factor of 30 because 30 can be written as a product of 15 times 2. This means that this is equal to 2 divided by 1, right? Because 30 is exactly twice the size of 15. Next, we have 16 and 12. 16 and 12 share several common factors. 4, for instance, is one of them. 2 also they share, but 4 is going to be the better one to choose here because 16 is 4 times 4. So if we divide it by 4, we get 4. If we divide 12 by 4, we get 3. So this fraction is equal to 4/3. 14/16 equal to 7/8. So these two numbers in this fraction of 25/36, we can't really reduce in that way, so we will just leave it. So what this comes down to is that these numbers are relatively prime. 25 and 36 share no common factors, and because they're relatively prime, that means that this fraction cannot be reduced. So we're going to have to leave it as 25 divided by 36, unfortunately. The next one, however, is a little bit better because 25 and 30 do have a common factor, and that common factor, of course, is 5. This fraction is equal to 5/6. 18 divided by 12. So now we've reduced all of our fractions to simpler forms, well, with the exception of 25 and 36, which are relatively prime numbers, so 25/36 has to remain. But the rest of them we have all reduced to simpler forms. So now we're in a position to analyze what kind of fractions these are, or what kind of relationships exist between these numbers. So all we're doing in this case is looking to see whether or not these are superparticular or sub-superparticular or neither. So remember, the superparticulars are those numbers which, when you write them out as a compound number, you end up with some number like 1, for instance, and 1 part. So this extra part could be 1/3, it could be 1 and 1/4, could be 1 and 1/5, regardless of whatever it actually is, as long as it remains with 1 part, right? 1 fractional part, then it is a superparticular. The subsuperparticular is simply the inverse relationship, where in order to get to 1, you need to add 1 part. So in this case, this is a sub-superparticular because to make 3/4 1, we add 1 part, right? 1/4, this makes it 1. So for that reason, 3/4 is a sub-superparticular. So we can label that. Next, we have 5/4. Now 5/4, if we write this out as a compound number, we know that we end up with 1, which is 4/4 plus 1/4 left over, which makes this indeed also a superparticular. Not a sub-superparticular, but a superparticular. Next, we have 2 and 1, or I should say 2/1, which we know is simply equal to 2. And because this is simply equal to 2, this makes this number neither, right? It's not sub-superparticular, it's not superparticular, it's neither. But the particular neither category that it falls into is, of course, the multiple. So we can call this neither, but really we recognize that it's a multiple, so I'll put that in parentheses. Next, we have 4/3. And it shouldn't surprise you that this also is a superparticular, because if we write this out as a compound number, we have 1 and 1/3, right? That's what this comes out to be. Therefore, because it's 1 with a fractional part, a single fractional part, 1/3, that makes it superparticular. Next, we have 7/8. Now, this one's not a superparticular because it's less than 1, but it lacks only 1 fractional part to be equal to 1. It's only missing 1/8, which makes this, of course, a sub-superparticular. Next, we have 25, 30, and 36, right? Which we can't reduce that any further, so this one's just going to be neither for now. Now, we might also analyze it to see whether or not it's a multiple form of something. But it doesn't seem to be, right? Because 36 and 25, neither of them fits inside the other, so it's not going to be a multiple form of any of these. Really, if you wanted to get down to what it actually is, it would actually be a form of the sub-superpartient, is what that would end up being, but we won't get into that right now. Okay, so 5/6. Well, this one is going to be sub-superparticular as well, right? This is sub-superparticular. Why? Because it's shy of being equal to 1 by 1/6. And then 3/2 is, of course, going to be superparticular. And it's superparticular of a particular kind, right? This one is, of course, going to be the sesquialter ratio of 3:2. Just like the very first one that we had here was the sub-sesquitertian, this one is the sesquialter. All right, and here we have, by the way, the sesquitertian, sub-sesquitertian over here, and then the sesquialter. All right, so there we have that exercise. I hope that that was helpful and clarifying. So next, let's take a look at the 10 fractions in epicycle C. Let's start with 27/18, the first one. Well, we should notice that both of these numbers are divisible by 9, so we're going to reduce them to a simpler form to be able to analyze them properly. As before, this is equal to 3/2. 8 and 12, both of these are divisible by 4. 25/10 is equal to 5/2. 5/6, of course, is just 5/6. 5 is a prime number. There's no way to reduce that further. 60/24 is equal to 5/2. 32/40, 4/5. 28/16, 7/4. 18 and 14, that's equal to 4/7. So you notice, by the way, these are sort of inverse fractions. 6 and 23. 23 is a prime number. We can do nothing with this. 14/5. 5 is a prime number. This cannot be reduced either. Okay, so that's the first step. And some of these are immediately recognizable as one form or another form. So 3/2, of course, is the sesquialter ratio. So that's going to be the super particular. So 3/2 sesquialter, super particular. 2/3 is the sub-super particular or the sub-sesquialter. 5/2, let's come back to that one. Let's just do all the ones that are 1 unit apart, because those are going to be super particulars of some kind, or sub-super particulars. So 5/6 is going to be a sub-super particular as well, because it's just shy of 1 by 1 fractional part. Same is true of 4/5. That's going to be a sub-super particular. And do we have any others? No, that looks like it's it. And we don't have any super particulars either. No. Okay, so the next thing we need to do is analyze the rest of these further. And the best way to do this is really to write them out as compound numbers. So 5/2, let's take that, write it out like so. So 5/2 is equal to 2 and 1/2. Isn't that right? And these came out to be the same, didn't they? So 5/2, yeah, 60, 12. Yeah, so these are the same. These are identical. And next we have 7/4, which can be written as 1 and 3/4, and 4/7 is simply going to be the subversion of whatever this is, and 14/5, which is equal to 2 and 4/5. All right, so once we do that, now we're in a better position to analyze these. So we know that these that have 2 in them are going to be multiple forms of something. Now this one has just a 1/2 left over, so it's a fractional part of 1. So that's going to make this a sesquialter of some kind, but it's going to be a multiple sesquialter. When the sesquialter is, of course, a superparticular, so this is the multiple superparticular. So there we have it. So both of these, 25/10 and 60/24, are multiple superparticulars. Next we have this one over here, 7/4. Now this one, you'll notice, is as a remainder. If we do the division, as a remainder we have 3/4. Or I should say, if we divide 7 and 4, we actually have a remainder of 3. So what this means is we have more than one fractional part remaining, which makes it not a superparticular, but a superpartient ratio. So this is a superpartient ratio. And this one, which is 2 and 4/5, because we have remaining more than a fractional part of 1, this is going to be a multiple superpartient. That makes 4/7 sub-superpartient, because 7/4 is a superpartient, 4/7 is a sub-superpartient. And then we have next to deal with 6/23, which we haven't talked about yet, but there it is. What do we do with this one? Well, the way to really do this is to ask ourselves, how many times does 6 go into 23? And if we do this division, you'll see 6, it goes into it 3 times, right? You can put 18 down here, and we're left with the remainder of 5, which means that 6 goes into 23 3 times, and we have a remainder of 5/6. Now, because we have a remainder of 5/6 here, so 3 and 5/6, this makes this a sub-multiple superpartient. This is a sub-multiple superpartient because it's like a multiple in the sense that one of the numbers goes into the other one several times, but because they're places are reversed and the numerator, can go into the denominator many times, then it's a submultiple. So that makes this one submultiple superpartient, because we end up with a remainder of 5/6, not 1/6. So because we have a remainder that's greater than one fractional part, it's a superpartient, but it's a submultiple superpartient because the 6 goes into 23 many times. And there we have it. And I hope, by the way, that you were able to get most of these correct in your journal. If you had trouble with them, you may want to go back and look at and see what you did wrong, just to make sure that that's clear before moving on. So there's just one more thing I would like to comment on before we end for today, and that's the essay assignment that I gave you in Epicycle D. You're going to continue to work on this essay over the next week, but I'd like to go ahead and make a few remarks about how to go about doing that. I do give you directions in the next cycle, but here are a few things that I really want to emphasize. First, you need to put in the appropriate amount of work into your outline. The outline is what's going to really make your essay easy or difficult to write. If you don't put enough time and detail into the outline, when you sit down to write, you'll be thinking through a lot of the things for the first time. Now, outlines can be a pain. I hated writing outlines as a student, but I've now, many years later, come to appreciate their tremendous usefulness. The reason outlines feel tedious is because you have to put in a lot of thought and effort, and you don't have a lot to show for it afterward. When you are writing, you at least have paragraphs, pages you can pull out and go, oh look, I worked hard, I've got one full page of writing, and you feel like you're coming close to completing the essay. The secret, though, is that when you're writing an outline, you're doing all the work ahead of time, and so it feels like you haven't done hardly anything because all you end up with is an outline. But with the outline, you can write your essay much, much more quickly. You don't have to think through things on the fly as you're writing because you've already thought them out. So all that you have to do, if you have a good enough outline, is set the outline beside you when you write, and then you just write. And you can just go straight through the outline. You don't even have to begin at the beginning if you don't want. If there's a particular paragraph you're dreading, you can start with that one, get that one out of the way, and then go back and finish the rest of your essay because you have a good outline. A good outline should cut the amount of time that it takes to write the essay probably in half if you have a good enough outline. So I offer that to you as a piece of advice. Work hard on the outline. Think of the outline as being at least half of the total work of the essay. Writing the essay should be the easy part. So think about that. Also, make sure that the essay is an elegant essay. Work hard to make your writing clear. Of course, use correct grammar and punctuation and all that. That should go without saying. But math essays are supposed to be things of elegance. And it doesn't matter whether or not the essay is a historical overview, something kind of like what we have here, or whether it's a treatise on a particular mathematical concept with mathematical proofs and things woven into it. It doesn't matter. Everything you do should be elegant. It doesn't have to be perfect. It doesn't have to be brilliant. It just needs to be presentable. So work hard this week on that, and we'll see you again after you've completed Cycle 5.